Hello friends, in this video we'll learn the different statistical tests that can be conducted in R. Now the contents of this lecture are as follows. After the introductory slide, we'll go to the description of the data, and then we start different types of testing and their R coding and learn about their R coding, like one sample t test, one sample median test, binomial test, chi-square test for goodness of fit, two sample independent t test, Wilcoxon Mann-Whitney U test, chi-square test for association between two categorical variable, and then Fisher's exact test, which is an alternative of chi-square test, homogeneity of variances or equal variances test, one way ANOVA, two way ANOVA. Then we will go for the non-parametric alternative of the one way ANOVA, that is Kruskal-Wallis test. Next we will go for paired t test and Wilcoxon signed rank sum test. Finally we will go for McNamara test and Friedman test, followed by finally conclude by one way MANOVA. Now let us go for the actual lecture. Now here we will explore the procedure about how to perform a number of statistical tests using R. Now in each section we will give a brief description about the objective of the statistical test and when it is used, as well as we will give an example showing the R commands, and we will explain the R output with brief interpretation of the output. And in deciding which test is appropriate, at the end of this lecture you can see for further clarification in the appendix portion. Now most of the example in this presentation will be conducted by using a data file which is called HSB2, that means high school and beyond. This data file contains 200 observations from a sample of high school students with demographic information about the students such as gender, which is written as female, socioeconomic status, ACS, ethnic group, that is race. The data file also contains a number of scores on some standardized test on reading, writing, mathematics and social studies. Now let us see the explanation of each of the variables in the data file in details. We have in total 11 variables. The first variable is the ID, which is a numeric variable, ID for the different respondent, which is numbered from 1 to 200, as there are 200 observations in the data. Then we have female variable, name is female, which represents the gender of the respondent, 1 for male and 0 for female. Then we have the ethnic group variable, which that is race, which is a numeric variable, and it has 4 values 1, 2, 3, 4. 1 stands for Hispanic, 2 for Asian, 3 for African, Amer, and 4 for white. Then we have socioeconomic status variable, which has 3 values 1, 2, 3. 1 for low status, low income people, 2 for middle income people, and 3 for high income categories people. Then we have school, type of school, which is written as SCHTYP, school type, where we have only two values, one for public school and two for private school. That means that as respondents who are attending public school and coded as 1, and 2 are coded for those respondent who are attending private school. Finally, we have program type variable, that is type of program they are attending. Here also we have three values, 1, 2, 3, 1 for general programs, 2 for academical program, and 3 for vocational program. Then we have reading, writing, and math, science, and social studies. These 5 variables contains the scores on some standardized test on these subjects, that is writing, reading, mathematics, science, and social studies. Now come to the different test procedure and how they have been conducted. They are conducted in R. Now first we start with one sample t-test. A one sample t-test allows us to test whether a sample mean of a normally distributed interval variable significantly differs from a hypothesized value. For example, in our HSB2 data file, we can test whether the average writing score of the respondents differ significantly from 50. So our null hypothesis is set as average writing score is 50. Now the alternative can be any of these three. Average writing score is not equal to 50, that means it is a two-tailed test. Now average writing score can be greater than 50, that is right tail test, and average writing score can be less than 50, that is left tail test. So first we should know the mean or average value of the writing score of the 200 respondent, and the R code is mean of the variable right, and the testing code for one sample t-test is t-test, that is the numeric vector R right. Now alternative, we have three alternative, two-sided for both tail test, greater and less for greater than a right tail test and left tail test, mu the hypothesized value of the average value, that is 50, and our the preset confidence level, that is confidence level is 0.99. There is a default confidence level in R. Now let us see how we can do in this t-test in R. Now first we have to import the data in R. For this, first let us set the working directory where the data file is stored in my PC. Now I have set my working directory. Now the data file is stored in SPSS format, so we need to load the library file for importing the data file in SPSS format. Our data file object is HSB2, our code is read SPSS, file choose, where the file manager will automatically come out and we can locate the file. Now as there are different levels of the variable, we should use the use value levels as true. Enter. Now the research methodology, here it is. Then statistical test, this is our HSB2 SAV spaces file. So data is imported. Now let us attach this data set to our workspace. Attach HSB2 and let us see the data visually. See the ID, female, race, ACS, SCH, TYP, program, read, write, math, science and social studies. So these are our variables. So for getting the mean value of the writing, we write the R command mean write. So average value of the respondent, average writing score of the respondent is 52.775. Let us check the actual. Let us now perform the t-test. Write alternative two sided sorry, we have done some yes. So this is our one sample t-test. Now t value is 4.14 and the corresponding probability value is very less, which is less than 0.05, that is 5% level. So the alternative hypothesis, that is true mean is not equal to 50, is accepted as a true. So we conclude that the mean of the variable right for this particular sample of the students is 52.77, which is statistically significantly different from the test value of 50. So we should conclude that this group of students has a significantly higher mean on writing test than 50. Now let us go for one sample median test. One sample median test allows us to test whether a sample median differs significantly from a hypothesized value. We will use the same variable right as we did in the one sample t-test example just now, but here we do not need to assume that the dependent variable is interval and normally distributed as we have done in the earlier one sample t-test. So here our null hypothesis is that median writing score is 50. Against alternative, the median score is not equal to 50 or greater than 50, or it is less than 50. Now let us look at the median value. Median right. So median value is 54, actual median value. Now for median test, the R code is Wilcox test right mu 54 alternative two sided. So our Wilcoxon signed rank test with continuity correction. Here the test value calculated value of the test statistics is 13177 and the corresponding probability value is less than 0.05, that is the level of significance. So we reject our null hypothesis and accept the alternative one, that is the true location is not equal to 50. That means the median score is not equal to 50. Then we go for binomial test. One sample binomial test will allow us to test whether the proportion of success on a two-level categorical dependent variable differs from a hypothesized value. For example, using our HSV2 data file, we can test whether the proportion of females differs significantly from 50%, that is the 0.5. So here our let us look at the character of the variable female. Structure, it is a factor variable, that means categorical variable. So we can not a numeric variable, so we cannot conduct directly the proportion test. So we have to convert the nature of the variable female to numerical variable. Now there is very simple command in R, that is as numeric function. By using as numeric function, we can easily convert the factor variable to numerical variable. Now if we write this female equals female, that means all the female in the respondent will be coded as internally 1 and male will be coded as 0. So see, the second object is coded as 1, here it is female. So now we can test the binomial test for looking at the or examining the proportion of female in the data set. So our R code is prop test sum female length female and the hypothesized value of the proportion, that is p equals 0.5. So we get our R results. So here the critical calculated value of the test statistic is 1.44 and the corresponding probability value is 0.22, which is higher than the level of significance, that is 0.05. So our null hypothesis, that is the true proportion value is equal to 50, a 0.5 is rejected, is not rejected, that is we accept that true p is equal to 0.5. The result thus indicates that there is no statistical difference. In other words, the proportion of female in this sample does not significantly differ from the hypothesis value of 50. Now we can check the actual number of female present in this data set, that is out of 200 respondent, if we how many females are there, simply by sum female, that is 109 females are there out of 200, and if we use the length function in R, we will get the total number, that is 200. So though apparently number of females is slightly higher than male, but statistically as such there is no difference. Now the chi-square test for goodness of fit. A chi-square goodness of fit test allow us to test whether the observed proportion for a categorical variable differs from a hypothesized proportion. For example, in our HSV2 data file, we can test the proportion of different ethnic group. For example, we believe that the population consists of 10% Hispanic, 10% Asian, 10% African American, and remaining 70% white. So we want to test whether the observed proportion from our sample differs significantly from those of the hypothesized proportion. So let us look at the actual number of different ethnic groups. So Hispanic has 24, Afro-Asian has 11, and African American 20, and white 145. So let us test the chi-square test for goodness of fit. Table, race, so our chi-squared test statistic is 5.02 and the corresponding probability value is 0.17, which is higher than the level of significance, that is 0.05. So the results indicate that the racial composition in our sample does not differ significantly from the hypothesized values that we have supplied, that is 10% Hispanic, Asian, and African American each, and the remaining 70% is white. Now, two sample independent sample t-test is used when we want to compare the means of a normally distributed interval dependent variable for two independent groups. For example, using the HSV2 data file, we can test whether the mean for writing is same for males and females. Now, in the two sample independent t-test, we need to check the equality of the variance of the two groups. The test will be different whether the variances of the two groups are equal or not. Let us first check the variance of the two groups. We do this by R command, that is, this will give the standard deviation of the score right in general, consisting of both males and female. Now if you want to get the average value of the standard deviation of the writing for female only, we use this R code. Now originally the data file contains female as female, but as we have changed the data file previously from categorical to numerical variable, we need to supply the numerical values for female, that is 1. So this is 8.133 is the standard deviation for writing score for females. Now the same value for male is 10.31. So slightly the variance of the male is higher than for female. Now let us do the actual let us examine this one by actual testing. that is Bhatt test between the writing score of female and male. That is right, female So this is our F test result to compare the variances of two groups, male and female, on the variable writing score. So here the calculated value of the F statistic is 1.61 with the probability value 0.01 or almost 0.02, which is less than the level of significance 0.05. So our null hypothesis that the true ratio of the variances is equal to 0 is rejected against in favor of is rejected in favor of the alternative hypothesis that is true ratio of the variances is not equal to 1. So we conclude that apparently the standard deviation of the two groups are close, however the test of the equalative variances indicate that the variance of the two groups are not equal. So we will use the t-test with unequal variances for comparing the average writing score of the two groups, male and female. So we use the t-test right against female var equal false. So this is the t-test result. So the OLH 2 sample t-test shows that the calculated value of the t statistic is minus 3.65 with the corresponding probability value is much lower than the level of significance. So our null hypothesis that the true differences in means equal to 0 is rejected in favor of the alternative 1, that is true differences in means is not equal to 0. So the result indicates clearly that there is a statistically significant difference between the mean writing score for males and females. More significantly, the writing score of the female is slightly higher than the writing score for the male. Now, Wilcoxon-Mann-Whitney test is a non-parametric analog to independent sample t-test and can be used when we do not assume that dependent variable is a normally distributed interval variable. We'll see that the R code for Wilcoxon-Mann-Whitney test is very much identical to that of the independent sample t-test. We will use the same data file and the same variables as we did in the independent sample t-test. Only difference is that we will not assume the normality about the dependent variable, that is writing score. So the R code is Wilcox test right female. Let us look at this result. Right so this is our Wilcoxon rank sum test with continuity correction. Here the calculated value of the test statistics is 3606 with corresponding probability value is much lower than the level of significance. So we reject our null hypothesis that true location shift is equal to 0. Rather we accept the alternative one, that is true location shift is not equal to 0. So the result suggests that there is a statistically significant difference between the underlying distribution of writing score of males with the writing scores of females. Now we'll go for another application of chi-square distribution, that is chi-square test to see if there is a relationship between two categorical variable. In R, the chi-square test code option is used to obtain the test statistic and its associated p-value. Using our data file HSB2, let us see if there is a relationship between the school type of school attended, that is school type, and students gender. Our null hypothesis is that there is no association between school type and female. Against the alternative, there is association, some sort of association between the two variables. So our calculated value of chi-square test statistic is 0.005, which is very less, with a high corresponding probability value, that is 0.98. So the result indicate that there is no statistically significant relationship between the type of school attended and the gender of the respondent. Now the Fisher exact test is used when you want to conduct the chi-square test, but one or more of the cells of the contingency table has an expected frequency of 5 or less. Please note that the chi-square test assumes that each cell has an expected frequency of 5 or more, but in Fisher exact test, as such, there is no such has no such assumptions and can be used regardless how small the expected frequency is in a contingency table. So let us look at the contingency table of school type and female. So this is our contingency table, 2 by 2 contingency table for school type and female. So if you want to go for Fisher exact test, we give this R code, Fisher dot test table SCH type female. So this is our Fisher exact test for count data. This result indicates that probability value, that is the probability value, is higher than the level of significance. So we accept our null hypothesis, that is the true odd ratio is equal to 1. So there is no association between the school type and female in the data set. Now homogeneity of the variances, that is we want to test the equality of the variances of two or more than two groups on a dependent interval dependent variable. The Bartlett test function provides a parametric k-sample test of equality of variances in R. The Fligner test provides a non-parametric test for the same. So if we want to test the Bartlett test of homogeneity of variances, we use this R code, and for non-parametric we use this Fligner test. Let us check in R Studio Bartlett test, write versus program. So the Bartlett state of variances of homogeneity of variances, here the Bartlett's case calculated value of the test statistic is 2.6 with corresponding probability value is 0.27, which is higher than the level of significance. So we accept our null hypothesis as a true, that is, the variances of the writing score of different program types are equal. Now the same test we can do by Fligner test, which is a non-parametric approach for checking the homogeneity of the variances. Fligner test. Here also the chi-square test statistic is 3.255 and the probability value, corresponding probability value is higher than the level of significance. So we conclude that there is no statistical difference in the variances of the different groups, writing score of the different groups. Now in RStudio, the HH function package provides a graphical test for homogeneity of the variances based on Brown-Forsyth. We use the HH package. Now let us load the HH package. Yes, now we use HOV, right? So here the Brown-Forsyth test statistic is 1.679 and the corresponding probability value is 0.189, which is higher than the level of significance, that is 0.05. So we cannot reject our null hypothesis, that is variances are identical. So we accept that the variances of the writing score are same across the different program types. Now an interesting feature of the HH package is that we can plot the variances of the three program types by HOV plot function, that is write program. Now let us zoom this picture. Yes, now see now come to the ANOVA analysis. In one way ANOVA one way ANOVA is used when we have a categorical independent variable with two or more categories and a normally distributed interval dependent variable, and we wish to test the differences in the means of the dependent variable broken down by the levels of the independent variable. For example, using the HSB2 data file, we wish to test whether the mean of write differs between the three program types. So first thing we need to do in R is to, before conducting the ANOVA, we need to do some examination of the assumptions behind the ANOVA analysis. First we need to check the presence of outlier. This can be done by box plot in R. There is box plot in R. The box command is box plot of the function of the variable write. To check, then we have to check the normality of the variable by Shapiro test, and at the same time we have to check the equality of the variances of the different types of programs, writing score of the different types of programs. Then if all these three assumptions are fulfilled, then we can apply the ANOVA on the model. So let us check the box plot. So this is the box plot. So see, there is no outlier in the variable writing. Then we go for the normality of the variable by Shapiro test. So Shapiro will normally test the here null hypothesis that the variable right is normally distributed against it is not normal. So the Shapiro calculated value of the Shapiro test statistic is 0.94 and the corresponding probability value is less than the level of significance. So the variable is not normally distribution. So we cannot apply ANOVA. However, for the sake of simplicity, for the moment we ignore this normality assumption in order to learn the R code how to apply the ANOVA. So we'll ignore this normality assumption momentarily. Now we have to check the homogeneity of the variances of different types of programs, writing scores of different types of programs by Bartlett test. Already we have performed this one. Again we are doing the same thing. So here this assumption is fulfilled as the probability value is higher than the level of significance. So we cannot reject the homogeneity of the variances. So the variances are equal across the different types of programs. Now we can apply the ANOVA. Now we write the ANOVA. This is one-way ANOVA, so we write AOV. In R, the AOV function provides the one-way or two-way ANOVA by fitting the model. Now we write the code, write so this is our R code. Now we stored this ANOVA as a object ANOVA 1. So ANOVA is performed. Let us see the results of the ANOVA by writing this summary function ANOVA 1. So see the f value is 21.27 with a very low corresponding probability value. So we get a statistically significant F statistics. So the one-way ANOVA result is significant. So our null hypothesis is that the means of the writing score of three different types of program, that is academic, vocational and general, are different. They are at least one of them is significantly different from others. Now in order to find out which group is different from the others, we have to go for post hoc analysis in ANOVA. That is performed by Tucky HSD function ANOVA 1. So see, we have done one the pairwise comparison, that is academic and general. The difference is 4.9. That means the average score of academic program is higher than general score, and this is statistically significant. Again, the vocation and general difference is minus 4.5. That means the general score is slightly higher than vocation, and it is also statistically significant. And academic score is also higher than vocation, as the difference is minus and it is statistically significant. So here we get that all the three different types of program have different average score, writing score. Now we can visualize the one-way ANOVA results more clearly by plotting the mean values with error bar, and that is being provided by gplot package in R. Let us try it. Gplots. Now plot means write program. So here we get the mean plot of different types of programs, general, academic and vocational. That is, see, the average value of the academic score is slightly higher than normal general score, and both academic and general is higher than the vocation score. So this is all about one-way ANOVA. Now two-way ANOVA is used when we have two categorical independent variable and normally distributed interval dependent variable, and we used to test the difference in the means of the dependent variable broken down by the levels of the independent variable. For example, using the HSB2 data file, we wish to test whether the mean of right differs among the three program types as well as their socio-economic status. So the R command is AOV write model fit program ACS, and we stored this as object ANOVA 2 in two-way ANOVA. So ANOVA 2 AOV let us look at the summary of the result. See, here we will get two F value. See, the F value for program type is statistically significant, and F value for socioeconomic status is not statistically significant. So the mean value of the writing score differs significantly across the different types of programs, but they do not differ significantly for different types of socioeconomic status. Now we can make pairwise comparison like one-way ANOVA by Taki HSD function, that is ANOVA 2. See, the differences already we have done previously, and all are statistically significant, but here the socioeconomic status, the differences are much less, and they are not statistically significant. Now the Kruskal-Wallis test is used as an alternative to one-way ANOVA, that is when we have one independent variable with two or more levels and an ordinal dependent variable. In other words, it is the non-parametric version of the ANOVA and generalized form of Mann-Whitney test method, since it permits two or more groups. Now we will use the same data file as we have done in one-way ANOVA example, and same variable for performing the Kruskal-Wallis test. The R code is Kruskal.test. Let us check it. Kruskal test, right. See, the Kruskal-Wallis chi-square test statistic is 34, and the corresponding probability value is much less than the level of significance. So we reject our null hypothesis, that is the average values of the writing score equal for all the program types, and we accept the alternative one, that is the writing score, average writing score differs across the different program types. Now if we want to perform the post hoc analysis in Kruskal-Wallis test, we need one package that is called PMC PMR in RStudio. So let us load the PMC MR package. So now this package is not installed by default, so we have to install this package first. So now the library PMC MR is loaded. Let us look at the R command post hoc Kraskal dot Nemeni test. Post hoc Kraskal Nemeni write and growth age program and if you want to make what tries are present, p values are not corrected, so there is some warning message. No, we can ignore the warning message. Let us look at the comparison. Academic and general, the difference between academic and general is statistically significant. Vocation and general is also statistically significant, and academic and vocation is also significant. So there is a statistically significance. The post hoc analysis shows that there is a difference in the writing score of the different types of programs. Now we want to test the paired t-test. A paired t-test is used when we have two related observations. There is two observations per subject, and we want to see if the means of these two normally distributed interval variables differ from one another. For example, using the HSB2 data file, we will test whether the mean of reading is equal to the mean of writing score. So first we will check the mean value of read and write by this R writing. So mean value of writing is 52.77 and the mean of read is 50. So apparently they are equal. Now let us test for the paired t-test. T-test write read. Now paired true. So this is our paired t-test results. So here the t-test statistic, calculated value of the test statistic is 0.86 and the corresponding probability value is 0.38, which is much higher than the level of significance. So we cannot reject our null hypothesis that the true difference in means is equal to 0, and rather we accept that the true difference in means is equal to 0. So the result indicates that the mean of reading is not significantly different from mean of writing. Now Wilcoxon signed rank sum test is the non-parametric version of the paired sample t-test. We'll use the Wilcoxon signed rank sum test when we do not wish to assume that the difference between the two variables is intervally and normally distributed. That is, the reading and writing score difference is not normally distributed. We'll use the same example as we have done in paired t-test, but will not assume that the difference between reading and write is interval and normally distributed. The R code is this. So let us try it in RStudio. Wilcox test read write paired true. So this is our Wilcoxon signed rank sum test with continuity correction. The calculated value of the test statistic is significantly high, that is 7.944. However, the probability value is 0.37, which is higher than the level of significance 0.05. So we cannot reject our null hypothesis that the true location shift is equal to 0. So the result suggests that there is no statistically significant difference between the reading and writing score. Now finally we will go for McNamara test. We perform McNamara test if we are interested in the marginal frequencies of the two binary outcomes. These binary outcomes may be the same outcome variable on matched pairs or two outcome variable from a single group. Now in our HSV2 data file, let us create two binary outcome in our dataset, that is high math and high read. These outcomes can be considered as a two-way contingency table. The null hypothesis is that the proportion of students in high math group is same as the proportion of students in high read group. That is, the contingency table is symmetric. Now high math variable is created for those respondents whose math score is above 60, and it will be coded as 1, else or otherwise it will be 0. That means high math, this variable will have value 1 if the math score is 60, and will have value 0 if the math score is less than 60. Similarly, we will create the high rate variable. Let us try it in RStudio, that is high math. If else math 60, yes 1, no 0. So this variable is created. Look here, say the first few respondents are coded as 0 because their math score is less than 60. See, first one is 60, 60, 60. Now we can get for example, see this similarly we can create the high rate. If else rate 60, yes 1, no equals 0. Sorry, we have done one mistake here. What's wrong? Let us try again. High rate yes, now it is created. See, high rate, the second respondent is coded as 1 because its score is above 1. For example, look here, rate it is 68, so it is coded as 1. Now we can test the McNamara test. The R code is McNamara test table high math high rate. Now look at the table first. Table high math high rate data HSB2. HSB2 high yes, this is the 2 by 2 contingency table for high rate and high math. Now we have to see the symmetry of this contingency table by McNamara test table high math high read. So this is the McNemar chi-square test with continuity corrections. Here the McNemar test statistic is 0.10 with a very high probability value, so we cannot reject the null hypothesis. So the contingency table is symmetric. That means the proportion of students in the high math group is the same as the proportion of students in the high read group. Now the Friedman test. We perform a Friedman test when we have one within subject independent variable with two or more levels and a dependent variable that is not interval and normally distributed but at least ordinal. We'll use this test to determine if there is a difference in the reading, writing and math scores. The null hypothesis in this test is that the distribution of the ranks of each type of scores, that is reading, writing and maths, are the same. To conduct Friedman test, the data needs to be a long format. So we use this R code Friedman test C-wind option. That means the read, writing and math will be tabulated as a different columns. So Friedman test C-wind read, write and math. Read, write and math. So this is the Friedman rank sum test. The calculated value of the chi-square Friedman chi-square test statistic is 0.64 with a very high probability value. That means we cannot reject the null hypothesis. So the null hypothesis is accepted, that is the distribution of the ranks of each type of score, that is reading, writing and math, are same. This is all about the different types of test that we can perform using this HSP2 data file. Thank you very much for watching this video.